Hello everyone and welcome to our YouTube channel. And yesterday we have uploaded our first introduction lecture where I have told you that we'll start with the electrostatic part. But from my previous teaching experience, what I have noticed that some concept related to the coordinate system and some mathematical concept will be really helpful to understand the electromagnetic theory. So that's why what we have decided that first we will spend few lecture to learn the coordinate system and the required mathematical concept, and then we will start with the electrostatic part. So today we'll talk about coordinate system. And when we say coordinate system means we will learn this four coordinate system. First we'll learn rectangular coordinate system and then polar coordinate system, and after then we'll talk about spherical polar coordinate system and cylindrical coordinate system. So after complete the coordinate system, we will also discuss few mathematical concept like how to write gradient of a scalar field in different coordinate system, and how to write a divergence curl of a vector field in different coordinate system, and how we can write a Laplace operator in different coordinate system. Then we will see the concept of Green's theorem and divergence theorem, and then we will also discuss how using Dirac delta function we can represent a point charge as a continuous charge, and also a continuous charge can be represented a discrete point charge uh, mm, by the summation of Dirac delta function. So this concept will actually help us to understand the electromagnetic theory. So that's why today we'll learn first coordinate system, and first we'll actually talk about a rectangular coordinate system. So let me write here a rectangular coordinate system. Rectangular coordinate system. So in rectangular coordinate system, usually we consider three orthogonal axes. So let's say these are three orthogonal axes: x-axis, this is y-axis, and this is z-axis. This is z-axis, and the point at which these three axes meet with each other, this point is called origin, and we represent this point as O. So this is the origin, and now with respect to this origin we can represent any point. And in rectangular coordinate system, usually we represent a point, any arbitrary point, by a set of coordinate system. Let's say consider a point in space. Consider a point, let's say this point, this is a P point, and this is an arbitrary point, and it has, let's say, coordinate of x, y, and z. So first we have to understand, when we write a coordinate of any point in terms of x, y, z, what does it represent actually? So for that, what we have to do, if we connect these 2 points, like if we connect this P point with the origin, we'll get a length vector. And then if we take the projection of this length vector on the x-axis, on the y-axis, on z-axis, that projection of this length on the x-axis, on the y-axis, on the z-axis will be respectively x, y, and z. X, y, and z. And also in rectangular coordinate system, we defined a set of unit vector. We defined a unit vector I cap. I cap always represent a unit vector along the positive x-axis, and j cap represent a unit vector along positive y-axis, and k cap represent a unit vector along positive z-axis. Okay, so once we know the coordinate of any point P with respect to this origin, and we also know the unit vector associated with each vector, each axis, then we can define the position vector of this point with respect to this origin. So let's write here the position vector. The position vector of point P, position vector of point P with respect to origin O is usually we represent this position vector in this way. If it is P point, then we'll write RP in suffix P. RP vector is equals to, how we can define this position vector of any point with respect to origin. So for that, what we have to write, first we have to write the x coordinate of this point. Let's say we want to write the position vector of P point. So first we'll write the x coordinate of this point. So in this case, x coordinate of the point P is x, and then we have to write a minus sign, and then we have to write the x coordinate of this origin. So in this case, origin has a coordinate 0 0 0. Is x coordinate, y coordinate, and z coordinate all are 0. So we'll write here 0, and then we have to multiply the unit vector along the x-axis, that is I cap. Similarly, we can write y component also. So for that, first we have to write the y coordinate of point P, and then a minus sign, and then we have to write the y coordinate of this origin. So in this case, y coordinate of origin is 0, so y minus 0 into z cap, and similar for z component, z minus 0 into k cap. So if we simplify it, what we'll get x I cap, and then y j cap, and z k cap. Z k cap. So this is the position vector of point P. Now imagine a situation like this whole universe, we want to represent this coordinate system. So in that case, what will be the value of x? X will be vary from minus infinity to plus infinity. Similarly, y will also vary from minus infinity to plus infinity, and z will also be vary from minus infinity to plus infinity. So now the question says, if we want to increase the value of x, so we can increase this value step by step. Now what will be the minimum value of this x? That minimum increment of x actually we represent by dx. Similarly, minimum increment of y we also represent dy, and minimum increment of z we represent by dz. And so if we consider another point, let's say Q point, which is just a nearby point to P, but if we want to go from P point to Q point, what we have to do, let's say we have to increase the x coordinate by dx, y coordinate by dy, and z coordinate by dz. So what will be the coordinate of this Q point? Let's say this is the Q point. Now if we want to go from P point to Q point, what we have to do, we have to increase the value of x by dx. So Q point will have a coordinate x plus dx. Similarly, when we goes from P point to Q point, if we increase the y value by dy, then the y coordinate of this Q point will be y plus dy, and similarly for z coordinate z plus dz. So we can write this Q point have a coordinate x plus dx, y plus dy, and z plus dz. Z plus dz. So now once we know the coordinate of Q point, then we can write the position vector of Q point just as the similar way as we have written the position vector of P point here. So the position vector of Q point, or of point Q, with respect to origin is RQ. So how we can write RQ? Just as since here you see P point has a coordinate xi x y z, so we have written this position vector with respect to origin xi cap y z cap z k cap. So similarly Q point have coordinate x plus dx y plus dy z plus dz. So if we want to write the position vector of this Q point with respect to this origin, so how we can write it? We can simply write it x plus dx, there is x coordinate of Q point into I cap, plus y coordinate of Q point into j cap, and z coordinate of Q point into k cap. Okay, so this is the position vector of Q point. So now if we added this P point and Q point, what we'll see, we'll get a unit vector, we'll get a vector here, this vector, and usually this vector is called actually elementary length vector in a rectangular coordinate system. Rectangular coordinate system. So the elementary length vector elementary length vector in rectangular coordinate system, in rectangular coordinate system can be written as so usually we represent this elementary length vector as a dl. This will be rp vector, this will be rq vector, and if this is the dl vector, so from the vector addition law we can simply write rp plus dl is equals to rq. So if we want to write dl vector, then we can write dl vector is equals to rq vector minus rp vector, and when you put the value of rq and rp, and then if you simplify it, so what we'll get dl vector is equals to dx I cap dy j cap and dz k cap. Dz k cap. So this is the elementary length vector in a rectangular coordinate system. Rectangular coordinate system where dx, dy, dz, they are the smallest possible increment along x-axis, y-axis, and z-axis, and the net elementary length vector in rectangular coordinate system can be written as dx I cap plus dy j cap plus dz k cap. Now the question is, in what kind of situations we need to consider this kind of elementary length vector? So let me just give you one example. Let's say we all learned in 12th class that if we have electric field and if we want to calculate potential difference in between 2 points, what definitions we use dv is equals to minus of E dot L vector. E dot L vector. But yeah, these definitions will be valid only for uniform electric field vector. Like let's say we have a uniform electric field vector like this, and then if we consider this is my length vector, so if we want to find out potential difference as 2 points, then when electric field is uniform, that's mean all the length over the length at each point electric field are actually have same value. But if it is non-uniform electric field, on the length if the electric field have value at different point, electric field have a different value, in that situations we cannot use this definition. So for that, what we have to do, we have to divide this large length into a small length, into a small length like this, and then over this length we can consider that electric field is almost constant. So then we can define this potential difference like this way: minus E dot dA. And then this is the potential difference over this length, and then next length and next length, and then we have to add it all the small part together. But since it is a continuous electric field, so what we can replace this summation by this integration. So for this kind of situations where there are a non-uniform electric field, and if we want to calculate the potential difference between 2 points in this electric field region, then we have to consider elementary length. And if this electric field is given in rectangular coordinate system, so first we have to consider this elementary length in rectangular coordinate system. So in that case we will write this elementary length in this way: dl is equals to dx I cap dy j cap dz k cap, and then we'll take the dot product with this given electric field, and then we have to integrate over the length that will be given in the questions. Okay, for this kind of situations we will use this concept of elementary length. And once we know this elementary length, next what we have to learn, that is concept of elementary area. So elementary area. What is the concept of elementary area? Let's say, let me give you one simple example. Let's say we have a square plate. We have a square plate, and it's a uniform charge distribution. It's every point per unit area is a sigma amount of charge, and let's say side of this square is A. So in this case, if I ask you what will be the total charge, then you can write total charge will be total area of this square, A square into sigma, and that will be the total charge. But if this charge distributions is non-uniform means at different point, if this charge distributions have different value, at this point it have some value, at this point it have per unit area. Let's say if we consider a point here, and if we consider a unit area here, so over this unit area the amount of charge, and here over the same area, unit area, the charge distribution is different. Then this type of charge distribution is called non-uniform charge distribution. So for this type of situations we cannot write total charge on the surface is this much. This will be wrong, and this will be only valid for uniform charge distribution. So when we have a non-uniform charge distribution, where sigma is function of some coordinate system, let's say if it is xy plane, then it will be a function of xy. So if it is non-uniform, then if we write simply sigma into a square, that will not give you the correct result. So for that, what we have to do, we have to actually divide this large area into small area. First we have to divide this large area into small area like this, and then now since this area is very, very small, so if we consider a point, so though this sigma is actually a variable over this large surface, but if this area is very, very small, then over this surface we can assume that the sigma is almost constant. Sigma will have some particular value, and that will be almost constant over this surface. So for that, what we'll do, we'll write the area of this part. Let's say this is a ds area, and then we'll write the value of sigma here. Same way we'll consider another elementary part here. We'll write the value of sigma here, and then we'll multiply this area, and then we'll add this all part together, and that will give us the total charge. Total charge, that's mean in this case, if we want to write total charge q, we have to write sigma into ds, and then we have to since sigma in this case is continuously distributed over the surface, so we can replace this summation by this integration. So for that, what we have to do, first we have to know how we can write this elementary area. Elementary area. So in rectangular coordinate system, we can actually define three type of plane: xy plane, xz plane, and zx plane. So let me just define this three plane first. Let's say this is xz plane, this is yz plane, and this is zx plane. So also let me draw the coordinate system. So let's say this is the y-axis, this is the x-axis, so x-axis, y-axis, and then this will be the z-axis. So in this case it will be xy plane. So on this plane you can see z is constant and x and y will be variable. So this type of plane is called xy plane. And then this plane, let me draw three coordinate system like this. But let's say this is a yz plane, so y, z, and this will be x. So you can see here y and z will be variable and x will be constant over this surface. And then third plane, and in this case let's say this is y, this is x, this is z, and this is x. So this will be the zx plane. Zx plane. So what we have learned in the here, that this dx, dy, dz, they are the smallest possible increment of x, y, and z, or other way you can say this is the projection of elementary length vector along x-axis, y-axis, and z-axis. So we can also define here the elementary length along y-axis, dy, and then elementary length along x-axis, dx. Now the area that will be formed by these two lengths, that area actually called the elementary area. That area, because these two lengths are the elementary length along x-axis and y-axis. So the area that will be formed by these two lengths, that will be the smallest possible area in this plane, and that plane is called elementary area. So what will be this elementary area? So for that we have to draw a parallel line from here, and also we have to draw a parallel line here. So this will be the elementary area in xy plane. So in this case, what we'll write? We'll write ds vector is equals to elementary area generally defined ds, and then since this surface, this area on the xy plane, so we'll write ds xy, and then you see here z actually constant, so we'll write z equals to, in this plane, since it is xy plane, so z will be 0. So how we can write, what will be the value of this? One side is dy, another side is, this side is dy, and this side is dx. So the area of this part will be dx into dy. Dx into dy. Now since this is an open surface, this surface does not close any volume, so this type of surface is called open surface. So for the open surface, if we want to write the directions of this area vector, so either we can write upward direction or downward direction, but it should be normal to this surface. So if it is xy plane, then upward or downward direction, upward will be plus k cap, downward will be minus k cap. So in this case we can write plus minus k cap. plus minus k cap. So if we want to represent the elementary area vector in xy plane, so we'll write in this way: elementary vector ds xy z equals to, if it is on the z equals to 0 plane, then we'll write z equals to 0 is equals to dx dy and plus minus k cap. Similarly, if we want to write the elementary length vector on this yz plane, so how we can define? We can draw a elementary length parallel to the z-axis dz, elementary length parallel to the y-axis dy, and then by this we can construct a area by these two lengths, and this length will be, this area will be the elementary area. So I have to draw a parallel line like this, and then this, and this will give you the elementary area on the yz plane. So in this case, this length is dz, this length is dy. So here we'll write ds vector in, now it is in yz plane, so we'll write y z. Now x equals to constant, and in this case x equals to 0. So this is equals to, will represent what will be the magnitude of this area. This will be simply dy and dz, and then again it's an open surface, so direction of this area vector will be either upward or downward. In this case we'll write plus minus I cap, plus minus I cap. And same way we can also define this elementary area on this zx plane. So for that, again we have to draw a parallel line to the x-axis, parallel line to the z-axis. This will be the dx, this length will be dz, and from there we can construct a elementary area. Yeah, and direction of this area vector will be either upward or downward. So on this plane we can write ds vector, elementary length vector, in this way ds. Now it is on zx plane, so we'll write zx, and on this plane y is equals to constant, and in this case y is 0. So this is equals to, we'll write, first we'll write the magnitude of this area vector, so this will be dx into dz, and then directions, since it is also open surface, so either we can take upward or downward. So in this case it will be plus minus j cap. Okay, plus minus j cap. So in this way, if we have a xy plane, or if you have a yz plane, or if you have a zx plane, so we can define elementary length on different surface. But most of the time we get a problem which is actually like a cubic surface. If we consider a cubic surface, cube generally have a 6 faces, and we'll see all these 3 surfaces, zx, yz, and zx plane, all 3 surfaces will come together on the cubic surface. So for that, let me draw a cube here. Let's say this is a cubic surface, it's a cube. This is a cube of side A. It's a cube of side A, and then consider the origin of the rectangular coordinate system lies at one corner of this cube, and side of this cube are parallel to the x-axis, y-axis, and z-axis. Okay. X-axis, y-axis, and z-axis. So in this case, you can see, if you take a look on the different surface of the of this cube, you will see all these 3 surfaces will be come on the same figure. See, if we take on the bottom surface in this, you can see z will be 0 on the bottom surface, and it is constant over the surface. Now x and y will be variable, so it will be xy plane. And then if we consider this surface, on this surface y will be constant, but you can see that x will be vary from, if it is cube side A, then x will vary from 0 to A, and z will also vary from 0 to A. So this surface will be zx plane. And this front surface, this surface it will be on this surface you can see x will be constant, but here y will vary from 0 to A, and z will also vary from 0 to A. So it will be yz surface. Okay, so on a cubic surface, if we consider a coordinate system in such a way so that the corner of this cubic surface lies at the origin of this coordinate system, and the side of the cube are parallel to the x-axis, y-axis, z-axis. So in this case, on the surface of the cube, we'll get all three kind of surface, all three kind of plane: so xz plane, yz plane, and zx plane. So we'll get a problem like this. If we have a cubic surface, and then electric field is written in terms of rectangular coordinate system, and then we need to calculate what will be the flux that will passes through this cubic surface or one particular surface. So for that, what we have to define that, like, we know the definition of electric flux: phi is equals to E dot A. But these definitions we can use when the electric field is uniform. But if it is electric field is non-uniform, then what we have to do? We have to divide this whole area into a elementary area. Now then, depending upon which plane, in which plane this area is lies, depending upon that, we have to define this elementary area in different way. If it is on the xy plane, then we'll define dx dy plus minus k cap. If it is on the yz plane, then we'll define dy dz plus minus I cap. If it is on the zx plane, then we'll define dx and dz plus minus j cap. And also we have to remember one more concept. Like, if it is open surface, then we can take the directions of area vector either upward or downward. But if it is closed surface, like cubic surface, this surface actually includes some volume. So in this case, if we want to write directions of area vector, what we have to do, we have to draw a unit. We have to draw a normal out of the surface. Normal. It should be normal, but it should be also outward to the surface. Let's say if we want to define the bottom surface, elementary area on the bottom surface, on this surface. So how we can define? On this surface, z is constant. So we have to draw a parallel line along y-axis, then we have to parallel line along x-axis. And then if we draw a parallel line of this length and this length, and this will give you a elementary area on this surface. So now what will be the area vector on this surface? This elementary length vector or elementary area vector. So we can define this elementary area vector ds. This is in xy plane, or this is on the xy plane. So we have to write dx xy. And now on this surface, z equals to 0. So we'll write z equals to 0, and then we'll write dx dy. Now since this is a closed surface, so if we want to write the unit vector associated with this area vector, then what we have to do, we have to first draw an outward normal on this surface. So if we want to draw outward normal on this surface, then which directions we have to draw? We have to draw downward. So this will be the outward normal to the surface, and these directions will be exactly opposite to the z-axis. So it will be minus k cap. Okay, it will be minus k cap. Similarly, if we want to define the elemental length on the top surface, so this is the elemental length on the bottom surface, and now if we want to define the elemental length on the top surface, so how we can define? So this surface and this surface, they are actually parallel to each other. Only the difference is on this surface z equals to 0, but on this surface z equals to a. In both the surface z are constant. On this surface z equals to 0, bottom surface z equals to 0, and at the top surface z equals to k. So in the same way, we can define the elementary area on the top surface. So for that, what we have to do, we have to draw a elementary length along y-axis parallel to the y-axis, and then we have to elementary length along x-axis, and from this with the help of these two length we can draw a elementary area vector like this. So this will be the elementary area vector in on the top surface. So in this case, again, if we want to find out the directions of this elementary length vector, what we have to do, we have to draw outward normal. So in this case, on the top surface, if we want to draw outward normal, it will go actually upward direction like this. Upward direction. So then how we can write the elementary area vector on this surface? So we'll write ds vector, and again this is a xy plane, so ds xy. Now z equals to constant, but in this case z equals to a. On this surface z equals to a, and then we'll write dx dy, and now this will be the directions of this elementary length vector. So elementary area vector, so it will be plus k cap, plus k cap. So similarly, you can also define the elementary length vector in other 4 surfaces. Let's say if we want to define the elementary area on this surface, what will be this elementary area? So on this surface, you can see y will be constant and y will be a. So if y is constant, then x and z will be variable, and the elementary length along x-axis is dx and elementary length along z-axis is dz. So we can write elementary area vector on this surface is equals to ds xz. Now on this surface, y is equals to constant, so y is equals to a, and this can be written as dx dz. Now what will be the direction? So it's a closed surface, we have to draw outward normal. So outward normal will be along this direction, it will be parallel to the positive y-axis. So in this case, it will be plus j cap. Plus j cap. And exactly if we want to define elementary length opposite to this surface, this is this face and the other face left side on this surface. So in this case, what will be the elementary area vector on this surface? On this surface, elementary area will be ds, and again it will also be the same xz plane, but the value of y will be in this case 0 here. So we'll write ds xz. Now y is constant, but in this case y will be 0, and we'll write dx dz. And if we want to draw a outward unit normal, this will be goes like this way, and this will be exactly opposite to this vector. So if this is plus j cap, then this will be minus j cap. So it will be minus j cap direction. Minus j cap. And same way, if we want to define the elementary length vector on the front surface, how we can define? And again, we have to draw a elementary length vector parallel to the z-axis, elementary length vector parallel to the y-axis, and on this surface x will be constant, front surface x will be constant. So this will be the directions of elementary length vector on the front surface. And if we want to write this vector, how we can write? We can write ds vector, and in this case it will be on the x will be constant, so it will be yz plane, so ds yz. And then for the front surface, x will be a, so xa is equals to dy dz, and this will be the parallel to the I cap, so it will be I cap direction. And from back surface, it will be exactly the same value. I'm writing here from the back surface, but the back surface it will be ds ds exactly same it will be there, but only the change will be this x will be 0 for the back surface. For the back surface it will be difficult to draw here, so you can imagine it, if it's the front surface, if it is x equals to plus f, on the back surface it will be x equals to minus x equals to 0, and directions will be only, now if for front surface if it is plus I cap, then for back surface it will be minus I cap. So you can write in this way, ds yz. Now x will be 0 for the back surface, and it can be written as dy dz, and then minus I cap. Okay, minus I cap. So cube have 6 surface, and on the 6th surface we have defined the elementary area vector. So this is a very important concept. We will see later when we talk about the electric flux. Sometimes the examiner asks only flux through the top surface, flux to the bottom surface, flux to the left surface or right surface or front surface or back surface. So for this type of situations, if it is asked for the top surface, then we have to first elementary length vector, we have elementary area vector, and then whatever electric field will given, we have to take a dot product with this electric field, and then we'll put z equals to a for this surface, and then we have to take the integration over this surface, and that will give the electric flux that will be passes through the top surface. So later we'll see how this concept is used to calculate electric flux or total charge on the surface. This kind of problem will solve later, but from here what you have to understood that how we can define the elementary area vector on different plane. Okay, once you know the elementary area vector, next what we can define elementary volume. So let me write here elementary volume. What is the concept of elementary volume? Let me again give you a simple example of, let's say we have a cubic surface. Okay, we have a cubic surface like this, and we have charge distribution over this volume, but in this case charge distribution is not uniform. Not uniform means it is not same over the all space inside the volume. At different space the charge per unit volume is different. So in this case we can write let's say if this is a coordinate system is set up like this, let's say this is x-axis, this is y-axis, and this is z-axis, then rho is a function of x, y, z. So at different point rho will be different, per unit volume charge will be different. In this case, if I ask you what will be the total charge, let's say side of the cube is here, and if I ask you what will be the total charge inside the cube, so if you write this way, the total volume a cube, and then charge per unit volume is given rho. So if you write a cube into rho, that will not give you correct result. That will give you only correct result when rho is independent of coordinate system. That's mean rho is uniform over the volume. But if rho is function of volume, rho is function of coordinate system, at different point rho have different value, then you cannot define, we cannot use this definition. So for that what we have to do, so if we want to calculate the total charge over the volume, then what we have to do, we have to divide this large volume into small volume, into smallest possible volume, and then over this volume we can consider this rho is almost constant, and then on the each elementary part we have to calculate the total charge, and then if we added the charge of all elementary part, and that will give the correct answer. But since rho is a function of x, y, z, that means it will be a continuous function. So if rho is continuous, then we can charge define like this: q is equals to rho into dv, where this dv is the elementary volume. And what is the elementary volume? So for that what we have to do, we have to break down this large volume into a small volume, and the smallest possible volume is called elementary volume. Smallest possible volume is called elementary volume. So how we can define the smallest possible elementary volume in rectangular coordinate system? For that, we know that elementary length along x-axis is dx, elementary length along y-axis is dy. So we can create an elementary area on this plane, and then if we also product this area with the elementary length along z-axis, and that will give actually a volume of a cuboid, whose volume will be like this. So this is the smallest possible volume that can be generated in rectangular coordinate system. And if we place this small volume side by side and up and down, eventually we'll get this large volume. So this volume of this portion is called elementary volume. So in this case, if we want to write elementary volume in rectangular coordinate system, so how we can define this? We can define this dV is equals to, first we have to write the area, and then we have to multiply with this area with this height. So area in this case will be dx dy, and then we have to also multiply with z to dz. So in rectangular coordinate system, elementary volume will be dx dy and dz. Dx dy and dz. Okay, so yeah, so this is it. And then what we have to remember here, what will be the limit of x, y and z. In general, if we want to represent the whole universe by this rectangular coordinate system, then the limit of x will be minus infinity to plus infinity. Similarly, the limit of y will be minus infinity to plus infinity, and the limit of z will be minus infinity to plus infinity. And also we have defined this I cap, j cap, k cap. They are the unit vector along x-axis, y-axis and z-axis, and they have some properties like I cap, j cap, k cap. So if we take a cross product with I cap with j cap, that will give you k cap. And then if you take a cross product with j cap of cross product of j cap with k cap, that will give you a unit vector along I cap. And same way, if you take a cross product of k cap with I cap, that will give you a unit vector along j cap. Along j cap. But if you reverse this cycle, if you take a cross product k cap with I cap, we take cross product in this way, like if you take a cross product of I cross j, that will give you k cap, and if you take cross product of j cross k, that will give you I cap, and if you take cross product of k with I cap, that will give you plus j cap. But if you reverse the direction, like if you take cross product let's say j cap with I cap, that will give you minus k cap, and if you take a cross product I cap with k cap, that will give you minus j cap, and if you take a cross product of k cap with j cap, that will give you minus I cap. Minus I cap. And also if we take a dot product I cap with I cap, that will give you 1, because these are the unit vector I cap. Like if you take a product of two vectors, what they represent? They represent the projection of one vector along the other vector. So if we take a position vector of I cap along the I cap, both are same vector and their magnitude 1, so in this case projection will be 1. And similarly j cap with j cap give you 1, and if you take dot product of k cap with k cap, that will give you 1. However, if you take a dot product with j cap, I cap with j cap, that will give you 0, because in this case you can see here x-axis and y-axis, they will be perpendicular to each other. That's mean if I cap along this direction, then j cap will be along this direction. So when you take projection of this j cap along x-axis, it will give you actually 0 projection. So dot product will be 0. And similarly, if you take dot product j cap with k cap, that will also give you 0. And then k cap with I cap, that will also give you 0. Okay. So I hope if you know these things related to the rectangular coordinate system, that will be enough to understand the electromagnetic theory. Next, we have to learn about 2D polar coordinate system. 2D polar coordinate system. Two-D polar coordinate system. Two-D polar coordinate system. So to define this 2D polar coordinate system, let me just draw a XY plane here. So this is your y-axis, x-axis, and this is the origin. Now if we consider a point on this plane, it's a P point, and it has a coordinate, let's say x and y. X and y. Now in the same point, if we want to represent in 2D polar coordinate system, then how we define it? For that, first we join this line, this 2-point P point with the origin. This distance is represented by r, and this r, the angle between this r and positive x-axis is defined as phi. Phi. So in according to polar coordinate system, if we want to write the coordinate of this point P, so we can write like this way, r and phi. R and phi. So if we represent this point in terms of rectangular coordinate system, then we'll represent x and y. And if we want to represent this point in terms of 2D polar coordinate system, according to 2D polar coordinate system, we can represent r phi. But what is the main point here? That is either if you represent this point in terms of 2D polar coordinate system or in rectangular coordinate system, both will represent the same point with respect to the same coordinate system. So there must be some relations between this x, y, and r phi. R phi and xy, they will be somehow related to each other. So for that, what I am doing here, I am just draw a perpendicular from this point, P point, on the x-axis, and also I am drawing a perpendicular on the y-axis from this point P. Now if the coordinate of this point, according to rectangular coordinate system, if the coordinate of point P is x and y, then what will be this length? This length will be x, and this length should be y. This length should be y. And so this, we have drawn a perpendicular from the point P on the x-axis and the y-axis. So this angle will be 90 degree, and this angle will also be 90 degree. So if we want to write the value of cos phi from this triangle, right angle triangle, so how we can define this cos phi? Cos phi is equals to base upon hypotenuse. So base is x and hypotenuse in this case r. So we'll get x is equals to r cos phi. X is equals to r cos phi. And similarly, if this angle is phi, then this angle will be 90 minus phi. And if this is 90 minus phi, this angle is 90, so this angle will be again phi. This angle will be phi. So if this angle is phi, and from this triangle, if I want to write the value of sine phi, how I can define the value of sine phi? Sine phi is equals to, it will be ratio of perpendicular divided by hypotenuse. So in this case, perpendicular will be y and hypotenuse will be r. So we can write y divided by r. Now this will give you y is equals to r sine phi. Y is equals to r sine phi. So now we get the relations between x, y and r phi. So what we can do, we can write the position vector of this point with respect to this origin. First we'll write in terms of xy, and then we'll replace this xy in terms of r and phi. So right here, the position vector of point P, the position vector of point P with respect to the origin O is RP vector is equals to xi cap yj cap. If we write in terms of x and y, then we can write this way, xi cap plus yj cap. Now we know the relations between x, and we have already written here x in terms of r phi and also y in terms of r phi. So we can replace this x and y in terms of r phi. So if we replace that, then what we'll get? We'll get rp, position vector of point P, in terms of 2D polar coordinate system, that is in terms of r and phi. So what we'll get here? We'll get r cos phi I cap plus r sin phi j cap. R sin phi j cap. Okay. So this will be the position vector of point P, arbitrary point P, whose coordinate according to 2D polar coordinate system is r and phi. Okay, so if I have any point whose coordinate is r and phi according to polar coordinate system, that if we want to write the position vector of this point, we can write in this way: rp is equals to r cos phi I cap plus r sin phi j cap. Now, as we have already noticed that when we discuss a rectangular coordinate system, we have defined a unit vector associated with each variable. There was 3 variables, x, y, and z, and we have defined 3 unit vector associated with each variable, I cap, j cap, k cap, and they are represent the direction along which x and y and z are actually increased. So similarly, we can also represent any other coordinate system. Let's say in this case, this position vector is a function of 2 variables, r and phi. So we can define 2 unit vector associated with each variable. So we can define a variable associated, unit vector associated with this r, and we can also define a unit vector associated with the phi. And these directions actually represent when phi is fixed, in which directions r will increase, and when r is fixed, in which directions phi will increase. Okay, so how to define this unit vector associated with each variable? So for that, first step, what we have to know, we have to know how to write the position vector in terms of these variables. So in this case, 2D polar coordinate system, we have a position vector in terms of r and phi. So we have 2 variables, so we can define 2 unit vector associated with each variable. Okay, so how we can define this? So let's write here the unit vector associated with R. So usually we represent by R cap. So R cap. And how we'll define this R cap? This is the general definitions of any coordinate system. If we know the position vector in any coordinate system, then we can define, let's say in any coordinate system, position vector is a function of n variable. Then in this coordinate system, we can define the n number of unit vector associated with each variable. So in this case, this position vector is a function of two variable r and phi, so we can define two unit vector. So first we'll define the unit vector associated with r, and how we can define this r cap is equals to, so first we have to take a partial differentiation of this position vector rp with respect to this variable r when phi is fixed. And then after differentiation, what we have to do, we have to divide the magnitude of this vector rp divided by here. Okay, so first we have to take the partial derivative of this position vector with respect to r, and then after the derivation, whatever vector we'll get, we have to divide this vector by its magnitude, and that will give us the unit vector associated with this variable r, which will represent, in this case we are representing it as a r cap. So r cap will be, so first we have to differentiate this position vector with respect to r. So if we differentiate this position vector rp with respect to r, keeping phi fixed, so what we'll get, cos phi I cap plus sin phi j cap. And then what we have to do, we have to divide this vector by its magnitude. So what will be the magnitude? Cos square phi plus sin square phi, under root cos square phi plus sin square phi. Now this cos square phi sin square phi is 1. So finally what we'll get, r cap is equals to cos phi I cap plus sin phi j cap. So this will be the unit vector associated with variable r, and in this case we represent this by r cap. So r cap is the associated unit vector associated with variable r, and how it is written here, r cap is equals to cos phi I cap plus sin phi j cap. Sin phi j cap. Same way we can also define the unit vector associated with the variable, another variable phi. So right here, the unit vector associated with variable phi. And in this case, we represent it as a phi cap. So how we'll define phi cap? So again, what we have to do, we have to take the partial differentiation of this position vector with respect to phi, keeping r fixed, and then we have to divide this vector by its magnitude. Del r phi by del phi. So when you differentiate this r position vector rp with respect to phi, keeping r fixed, what we'll get? We'll get minus r sin phi I cap plus r cos phi j cap, and then what we have to do, we have to divide by its magnitude. So it will be magnitude of this vector will be r square sine square phi plus r square cos square phi. Now see this denominator, both the term have r square, so we can take r square common, and when you take it outside the square root it will give r, and in numerator also you can see here both the term have r, so r will cancel out from the numerator and denominator. So finally what we'll get, and in denominator will get sine square plus cos square phi, that will give you 1. So finally we'll get phi cap is equals to minus sine phi I cap plus cos phi j cap, cos phi j cap, and this will be the unit vector associated with phi, associated with variable phi. So what does mean? It's mean that if we keep the value of r fixed, then at that point in which directions phi will increase, that will define by this unit vector. So this directions of this unit vector give you the direction of phi, in which directions phi will increase. In which directions phi will increase, that will give that directions will be given by the this unit vector phi cap. Okay, so this also we can understood by a small figure. So let me draw a circle here. Let's say this is a xy plane, and then draw a circle in this xy plane which center say at the origin of this coordinate system. Okay, the center of the circle is at the center of the coordinate system. So now if we ask you what will be the directions of r cap and theta cap at this position, at this position, at this position, at this position, and at this position. So for that what we have to do, we already derived the value of r cap and theta cap. So let me write here again. R cap we have defined cos phi plus sin phi j cap, and phi cap we have defined as minus sin phi cap plus cos phi j cap. Okay, cos phi j cap. And what is the phi? If we consider any point, here we have defined already. If we consider any point, let's say this point P, so this r vector, the angle between r vector and the positive x-axis, that will give you the value of phi. So in this case, if we consider this point, and if we join this point with the origin, so it will be parallel to the x-axis. So in this case, phi will be 0. So for this point, phi will be 0. For this point, phi will be 90 degree. So if you added this point with the origin, it will be parallel to the y-axis. So the angle between these two, this r and this positive x-axis, will be 90 degrees. So for this point, phi is equals to 90 degree. And similarly for this point, this angle phi will be phi 180. And for this point, you add it like this, this will be your r. Now this r will make this angle with the positive x-axis, and this angle will be phi is equals to 270 degree. Okay, so we know the value of phi, and you see r cap and phi cap, it is only function of phi. So what you need only, if you know the phi cap, if you know the value of phi, then you can define the value of you can define the directions of this r cap phi cap at different position. So first, if you define the phi cap directions of r cap and phi cap at this position, so you just put in this equation phi is equals to 0. So when you put phi equals to 0, what will get here? R cap will give you cos phi equals, when phi is 0, cos phi will be 1 and sin phi will be 0. So r cap will be I cap. So for this point, r cap will be along this direction. This will be direction of r cap. And what will be the directions of phi cap? See, if you put here value phi is equals to 0 in this equation, what you'll get? Sin phi 0, cos phi equals to 1, cos phi is equals to, if you put 0, then cos 0 will give you 1. So phi cap will be plus j cap. So directions of phi cap will be along this direction. Positive j axis phi cap. Phi cap. Similarly, you can also find out here for this point what you have to do. You have to put this value of phi 90 in this equation. When you put the value of 90 in these equations, will get r cap parallel to the y-axis, that is plus j cap direction. This will be the r cap direction, and phi cap will be minus I cap. So this will be the direction of phi cap at this position. Same way at this position, what you have to do, if you want to calculate r cap phi cap at this position, you have to put the value of phi 180 in these equations, and when you put the value of phi is equals to 180, what you will get? You get r cap will be minus I cap direction, and phi cap will be minus j cap direction. Minus j cap direction. And for this point also, r cap will be minus j cap direction, and phi cap will be plus I direction. Plus I direction. So you see, at every point, if you take a look on the directions of r cap, it will be always radially outward. R cap will be always radially outward. And let's say if we want to if we keep the value of phi fixed at this point, and if we want to increase the radius, that will be also increase in this direction, positive x direction. So that's why I'm telling that this r cap will represent the direction in which r will increase when phi is fixed. And same way, if you keep the value of r fixed, and if you just increase the value of phi, this point will start moving in this direction. So this will give you the directions of this phi cap will give you the directions of phi cap will give you the direction along which the phi actually increase. Phi is increased. So, and one more thing, you can take a look here. R cap will be always radial outward, and phi cap will be always tangential to the surface, to the circle, and anti-clockwise direction. Anti-clockwise direction. And at every point, you can see these two vectors will be perpendicular with each other. That also you can confirm yourself. If you take the dot product of this r cap and phi cap, you will get actually 0. So these are unit vector. Magnitude of this vector will be non-zero, but the dot product is 0. That simply suggests that these two vectors will be perpendicular with each other. At every point, they will be perpendicular with each other. Okay. So now if I want to ask you, what will be the directions of this r cap and phi cap at this position? Just think about it. How can you represent the directions of r cap and phi cap at this position? So what we have noticed that the r cap will be always radial outward, and phi cap will be always perpendicular to the r cap, and it will be tangent to the surface and anti-clockwise direction. So that's mean first we have to draw the r cap direction. First we have to draw the r cap direction, and in this case r cap will be along this direction. R cap will be along this direction, and then what we have to do, we have to draw a tangent to this surface at this point, but anti-clockwise direction, so we'll be having this direction. So this will be the directions of r cap, and this will be the direction of phi cap. Okay, so this way you can define the unit vector at any point on this circle. And this 2D polar coordinate actually we will use when this kind of situations will appear, say circular loop or say 2D a circular disk. For that kind of problem, we will always use this 2D polar coordinate system. And sometimes we have also defined this r cap and directions of phi cap. And if you know these directions of r cap and phi cap, then it will be easy. You can easily solve the problem actually. Okay. So this is the directions related to the r cap and phi cap, and they will be always perpendicular with each other, and r cap will be always radially outward, and phi cap will be tangential to the surface and will be always in anti-clockwise direction. Now, once you know these directions of r cap and phi cap, then what we can define the elementary length vector and elementary area vector in 2D polar coordinate system. So let me first define the elementary length vector, and then we'll define elementary area vector. So right here, elementary length vector. Elementary length vector. Okay, so let me just define one by one. First, we'll define elementary length vector along R, and then we'll define elementary length vector along phi. So we know the directions of R, we know the directions of phi. So now we have to define the elementary length vector along r cap and along phi cap. So for that, what I am doing here, I am drawing a two concentric circle. On the same plane. Let's say the inner circle has a radius r and outer circle has a radius r plus dr. R plus dr. And what is dr here? So let's imagine a situation like that. This universe is plane. Universe is plane, and we want to represent this universe by this 2D polar coordinate system. So in this case, the value of r will be 0 to infinity. So now if we want to increase the value of r, so we can increase step by step, and the smallest possible increment is represented by dr. The smallest possible increment of r is represented by dr. So now the question says, let's say you are on the inner circle, at any position on the inner circle, at any point on the inner circle. Now, if you want to go from inner circle to outer circle along the r cap direction, how much distance you have to travel? If you are here, then you want to go from here to here. In r cap directions mean radial outward direction, so here to here. If you are here, then you have to go from here to here in r cap direction. If you are here, then you have to go from here to here in r cap direction, like this. If you are here, then you have to go from here to here in r cap direction. So what will be this length? In every point, this length will be dr. In every point, this length will be dr. And what will be direction? Directions will be r cap. So these are this is called elementary length vector along r cap. And in general, we represent this dlr. Elementary length vector along r will represent as dr r cap. Okay, dr r cap. Okay, good. Then let me draw another case. Like this is your XY plane, and we have a circle like this. And then consider a value of point. Consider a point P here on the circle, and radius of this circle, let's say R. Radius of the circle R, and this R makes an angle with the positive x-axis phi. Okay? Positive x-axis phi. Now, if I increase this angle by small angle d phi, keeping the value of R fixed. If we increase the value of phi by a small angle d phi, keeping the value of R fixed, then this point, actually it will not be here, it will be shifted from this point to this point. So when we increase this value of phi by a small angle d phi, keeping the value of R fixed, so this point will be shifted from here to here. And already I have shown in last phase that this is the directions of phi cap. If we draw a pen vector like this, this is the directions of phi cap. So when you increase this value of phi by a small angle d phi, so for that actually this point will be shifted from this point to this point along the phi cap direction. So this will give you the elementary length vector along phi cap. Along phi cap, and we define as dl phi. So what will be the elemental length vector along dl phi? So dl phi in this case, so this angle is d phi and this length is r, so this length will be r d phi. R d phi phi cap. R d phi phi cap. So this will be the elemental length vector along phi cap. So once we know the elemental length vector along r cap, along phi cap, then we can write the general elemental length vector in 2D polar coordinate system. So in 2D polar coordinate system, general elemental length vector will be dl vector is equals to r component of elemental length dr r cap plus phi component r d phi phi cap. R d phi phi cap. Okay. So whenever this type of situations will come, when let's say we have a circular loop or we have a circular disk. So if we want to write the elemental length along r, then we'll write dr r cap. If we want to write elemental length along phi, then we'll write r d phi. R d phi. And if we want to write total elemental length, then we're going to write with dr r cap and r d phi phi cap. R d phi phi cap. Now once we know this elemental length along r and along phi, now we can define what will be the elementary area in 2D polar coordinate system. Elementary area 2D polar coordinate system. Polar coordinate system. Polar coordinate system. So for that, again, let me just draw a xy axis first. Let's say this is x-axis and this is y-axis, and imagine this plane is actually inverse is plane. So we want to elementary area, so large area. If this whole inverse is plane, then it will be a large area. Now we want to divide this large area into small elementary area, and what will be the smallest possible elementary area in terms of polar coordinate. If we want to write in rectangular coordinate, what we'll write? We'll write simply dx dy. But if we want to write the same area vector in terms of polar coordinate, then how we can write this? For that, let me just define a point in terms of polar coordinate. Let's say this point. So a point whose coordinate is according to polar coordinate r and phi. R and phi, that's mean this distance is r and this angle is phi. Angle is phi. Now, if I want to increase the value of r, keeping phi fixed by the value of by dr, then we can represent this thing here. At this point, dr will increase this direction, and this increment is simply the elementary length of r, the smallest possible increment of r. So this will be the dr. Dr. And then again come back here. Now, first what we have done, we have kept the value of phi fixed, and we have increased the value of r by dr. So we'll go from this point to this point. Now again come back here, and if we want to increase the value of phi, keeping the value of r fixed, then we'll move in this direction. We'll move in this direction. And what will be this length? If we increase the value of phi by d phi, keeping the r fixed, then we'll reach this point, and this length will be in this case r d phi. R d phi. Now, if we, since this dr and this d phi is very, very small, so if we draw a parallel line here and a parallel line here, so this will give you a elementary area in 2D polar coordinate system. And what will be this area? We can write almost this length is equals to this length, and this length is equals to this length, because this dr and dr d phi is very, very small. So in this case, the total area of this part will be the elementary area in polar coordinate system, and we'll write is just product of these two length. It will be r dr d phi. R dr d phi. Now 2D plane will be open surface. So in this case, if it is xy plane, then we can write plus minus k cap. If it is zx plane, then we'll write plus minus j cap. So in general, we're writing here n cap. N cap will be the normal to this surface, either upward or downward. Okay. So this will be the elementary area vector in 2D polar coordinate system. Okay. Now it's 2D plane, so we cannot define volume. So we have to learn up to this point. And then again, if we want to represent this whole universe by this 2D polar coordinate system, then what will be the limit of r? We consider the center of this universe lies at the center of this coordinate system lies at the center. I mean, the coordinate system of this 2D polar coordinate system lies at the center of this plane. Then we can write the value of variable of limit of the variable r will be from minus 0 to infinity, from 0 to infinity. And what will be the value of phi? The limit of phi will be 0 to pi. 0 to pi. Okay. So for rectangular coordinate system and 2D polar coordinate system, this whatever we have learned, that will be enough to understand the electromagnetic theory. And in next class, we'll talk about other two coordinate system. So for today's class, this is fine, and in next class we'll talk about other two coordinate systems. So bye bye, see you in the next class.